Oh, hi there. Thanks for showing up for your learning. I do appreciate you arriving periodically to absorb some new math knowledge. Let's take a look at this idea here. If we were thinking about the height of this ladybug over time, what would happen if the bike tire were a little bigger? What would happen to its height? Would its minimum change? No, but it would change the maximum height. Would it change the horizontal axis? Yeah, it would change the horizontal axis. Horizontal axis would be higher if the bike tire were bigger. What if the bike were traveling fast? How would the function change? Yeah, the period would be shorter. It would go up and down quicker. And if it was traveling slower, it would be stretched out more. Good. And then, hard to think about how you would change the height of the axis without changing the amplitude, right? Unless you had the bike like ride up on a ramp or something, then it might be over the ground and then come down or something. But yeah, you want to think about these types of situations, and we'll be thinking about that as we look at the different transformations today. So, if we're looking at transform sinusoidal functions, you're going to feel successful if you can look at an equation and say these are the transformations that have been applied to sine of x or cosine of x, and also describe the properties of those sinusoidal functions, such as amplitude, period, horizontal axis, and phase shift, and the effects of the transformations on those properties. And finally, you'll be successful if you can graph them. That'll be the way we look at your abilities in this area. So if we remember that transformations are going to show up in this way, one tip, and this is good to emphasize, if you are dumping things into Desmos, Desmos does not like square brackets here. Use just another set of round brackets. Otherwise, this is where your transformations show up. And when we're looking at sinusoidal functions, they'll either look like this. F of x is equal to a sine of bracket k bracket x minus d bracket bracket plus c. Or they might look like g of x, which is equal to a cosine of k x minus d and bracket bracket plus c. So these are the two ways that you're going to see these functions appearing for you. And what to say about those? Well, while you're copying these down, I'll kind of talk through this. It looks like this is math class. Where did all the numbers go? I see a big sea of letters. Just remember, sine is a mathematical operation. You're going to do that to some angle, something that's functioning like an angle. Although now x will frequently be time or horizontal distance or something like that. But in any case, sine is an operation we do to x, but then we're going to add or subtract something from x. We're going to multiply x by something. And then after we're done evaluating sine, so BEDMAS-wise, all this happens first because it's inside brackets. After we're done evaluating sine, then we might multiply the result of sine by a, and then we might add or subtract something from the result of multiplying the sine of that great big thing. So it's one of those elephants that we eat bite by bite. The first bite you do would be evaluate x minus d. The next bite you would do would be multiplying by k. The next bite you would do would be take the sine of that. And then you would multiply the result by a, and then add or subtract c from that. So that's BEDMAS-wise what we are going to be doing. And so they look like this. There you go. But again, prefers round brackets if you're using Desmos. Those are not Desmos friendly. Okay. And we'll also notice sine and cosine are just transformations of one another. They're just shifted by 90 degrees relative to one another. So when we think about the a value, which one of those properties that we have for our periodic functions is going to be influenced by the a value? Will it change, giving obvious wrong answers first? The horizontal axis? Yeah, it will change the amplitude. The distance between the maximum and the minimum is going to rise when we change a. So here you have a graph of y is equal to sine x. This graph is in radians, you'll notice. It's going up to 2 pi, but in any case, you'll notice that the maximum here is at 1 for sine of x. If you multiply that by an a transformation of 2, that's going to double the amplitude. If you have 1/2 sine of x, well, that would look like this. And its amplitude would only be 1/2. So it's directly changing the amplitude. A is amplitude. So that one's fairly straightforward to remember. Here's cosine. If you got to graph cosine on your own yesterday, you'll notice that its y-intercept starts at 1 compared to sine, whose y-intercept starts at 0. And cosine goes down and reaches its minimum at 180 degrees. Here is cosine of x, and here's 2 cosine of x. Just notice that the amplitude has been doubled, but all of the x-intercepts are the same. Doesn't matter if you change the a value. The x-intercepts in this case are where it touches the horizontal axis. So let's keep going. Oh, zoom out. There we go. The a value changes the amplitude. So in these cases, if you were going to graph 4 sine of x, f of x is 4 sine of x, what would the amplitude be? 4. Good. Yeah. So the amplitude here is amplitude. Well, that's pretty easy. And if you're working visually, you can absolutely use that to error check your graph and make sure that you're hitting the right points at your maximums and minimums. How about this one? F of x is equal to 1/3 cosine of x. What's the amplitude of that function? 1/3, yeah, okay. Amplitude equals 1/3. Yeah, so that's going to be a very gentle wave. Then, which of the properties of the sinusoidal functions is the k value going to affect? The period, right. Now, the period here that they're showing is 2 pi. Again, fancy math people will be really happy with that. We're going to see 360 degrees there. That's the normal period of sine. It takes 360 degrees around the circle to get back to the starting point, and then it goes through its cycles off to infinity, going in a circle. But if you add that k transformation, that's going to influence the period. So how does that work? Well, if the period is normally 360 and k divides our x values, its k is going to compress. So these little formulas here, you absolutely want to have written down or circled or highlighted, put arrows next to them. Use these 2 mini formulas here to either calculate the period or calculate the k value. They're just rearrangements of one another. You'll see if I take the first formula, this one, and multiply both sides by the period and then divide both sides by k, I will get this formula. So they're the same thing. But you'd use one if you were looking visually at a graph and you had to say, what is the equation of that graph? You can read the period by seeing the length of one cycle and then finding the k value. With this one here, if you know the k value, then you can calculate the period very easily. And this one is useful when you're graphing. This one is useful when you're creating an equation. Maybe I'll write that down, actually. So you might want to copy this down. So in these 2 examples, you have f of x is equal to sine 2x. What's the period of that function? $180? Good. So that one has a period of 180. And how about the other one? cosine of 1/2 x, what's its period? 720. Very good. Yeah, 720. Good. Very good. So let's get those in here. So we are going to have here the period, and you just work it out. 360 divided by 2 equals 180. And you'll notice I'm going to tend to use numbers that divide 360 very nicely here to go nicely on you. And fortunately, 360 is a number very rich in factors. That's why we have 360 degrees. It's very easy to divide it evenly by a lot of numbers. How about cosine 1/2 of x? Well, that one you would say the period is 360 divided by 1/2, and then you would flip and multiply. 360 times 2 equals 720. 720. Now, if I show you this equation here, what was the k value? Let's see if I can get you some information to go on there. This point here, 7.5. This point here, let's get some x-intercepts, 37.5. What was the k value? So I'm showing you two of the x-intercepts. Happens to have how much, what's the length of one cycle? 30. So we can find the length of one cycle visually here, finding two equivalent points. Note that it would be a mistake to use that point and say that 7.5 to 27.5 is a period, because we want to not only be at the same value, but be also rising or also falling. Like it should be parallel, the same point along the cycle. So we have the cycle length here is 30. If we're doing that, then we would use this formula here. We would say, I know the period is 30. Oh, sorry, we would use this one here, 360. So you take 360, divide it by 30, and get 12. Let's see if Oscar is correct. Oh, look at that. 12 was the k value. Oscar was correct. And then we carry on. The k value here. So the k value, one trick about the k value is whatever your k value, that's how many cycles you will have within 360 degrees. So that's one way to think about that.
Question.
Yeah.
When we're graphing, how do we know how long 360 degrees is?
Like, how do you mean how long?
Like the question you gave us earlier. The
Yeah.
period was 30 degrees. Like, how do I know what a 30 degrees is?
30 degrees? Oh, no, 30 x units, like the cycle.
Oh,
So
30.
Yeah, so that would be 30 units in the x. So if I ask you to graph 2 full cycles of it, you might start your graph at negative 30 and positive 30, or 0 to 60. And then you could show 2 full cycles.
Yeah, but on Desmos here, it's much longer than that.
What? I think you're still in radians.
Oh, you want us to be in degrees?
Yeah, we're not fancy math people. Well, we are. We're becoming fancy math people. There you go. All right, let's keep going. Okay, now this d value. D values, if you recall, do this thing of just taking the whole shape and moving it left or right. So that's going to influence where these functions touch the y-axis, like where their y-intercept is, because that's going to flow up or down as d changes. And it's going to change what we call the phase shift. So the phase shift, this new definition here, just is basically saying where are we starting there. This is something that's going to shake out in your table of values, and working that out from graphs. Like if you look at a graph and you say, okay, I need to find the d value here. I will show you a few different strategies to calculate that tomorrow. Again, this is something that's very tricky until it's not. When I first started playing guitar, I didn't like it very much and my fingers hurt. Now I quite like it, and I can sometimes, if I'm lucky, make some music. So just need practice. So the d is associated with phase shift. So if we had to find the y-intercept and the phase shift of the following, how would we find the y-intercept of these functions? How would we describe the phase shift? Well, let me tell you how we would describe the phase shift. Okay. You would describe it as a transformation. So if I told you that to graph sine x plus 45, what direction and by how much has that been shifted?
That would to the negative direction, of course.
Okay, so we pulled the whole function to the negative direction, or if I'm doing towards the left, 45 units. Great. So this one is shifted 45 units left. Or if you call that in the negative direction, that's fine. Now, how do you find the y-intercept? If I had this equation, y equals 3x plus 6, what's the y-intercept? 6. And you just read it off of there, right? But let's say you didn't remember that y equals mx plus b and that b is always the y-intercept. Like I'm sure some of your fellow classmates forgot that piece of information, but are now like, oh yeah. But if you did forget that, how could you calculate the y-intercept of any function, given some function? I can't just simply read it off of that very easily. There you go. You just sub in 0 for x to find a y-intercept. Because here's my xy plane, and the value of x along the y-intercept is always 0. This is the line x equals 0. So substitute in 0 to the function and find it. So someone find for me, what's the y-intercept of this function? Give me an exact value, please. This is y-intercept. The y-intercept is f at 0 is equal to 1 over root 2. Because you would have sine of 0 plus 45. Sine 45 is 1 over root 2. So there you go. That's it. So then, if you were looking at your parent function like this, effectively what's happened is this is the point here, 45 degrees. And that point has been pulled to become the new y-intercept. And then it would go up from there and then come flowing down. Okay, carrying on. Now, how about this one? F of x is equal to cosine x minus 30. Describe for me the phase shift in terms of which direction it's been shifted.
To the right.
Yeah. Shift right 30. And what's the new y-intercept?
No.
What's the new y-intercept now? Oh, yeah, cosine. Root 3 over 2. Yeah. So the new y-intercept is root 3 over 2. Let's take a look at that factoid in Desmos here. So if I go ahead, open this up, and I graph y is equal to cosine of x minus d. Okay. I'm going to add a slider for d, and we're going to have to zoom quite a lot in because there we go. And then I'm going to let d slide all the way up to 30. Then as I play that, notice that it comes down. And as soon as we get to 30, we're there. So there's root 3 over 2, 0.866. If we have a more exciting K transformation like 10, then you would see the factors in there a little clearer. Okay, let's go. Now, the C value. Which property of the sinusoidal functions is the C value going to affect?
Changes the axis.
Changes the horizontal axis. Yeah. It basically takes your whole function, moves it upwards or downwards like a forklift. So if we lift the whole function up, the horizontal axis is going to go up. So if we connect the C value to these different visualizations of the horizontal axis, we'll see, yeah, this is f of x is equal to cosine of x and nicely centered around the x-axis. Here is f of x is cosine of x minus 5. The horizontal axis shifted down by 5. And up here, cosine of x plus 5 If I draw the line y equals 5 there, you'll notice that that symmetrically cuts the function in half. There. So c is the vertical shift, and it is the equation of the axis. C equals the like if you say y equals c, then that's the equation of your axis. So what's the so the vertical shift here for these two functions? Sine of x plus 2. Shift up by 2. And the y equals 2 is the equation of the horizontal axis. Shift down 3. Y equals minus 3 is the equation of our horizontal axis. Now, looking at the domain and range, you're going to think about how do these transforms affect the domain and range. So the domain is only ever limited by your application scenarios. X always goes off to infinity. You can always go around and around the circle an infinite number of times. Or go backwards in time, backwards around the circle an infinite number of times. Of course, different application scenarios will have limits on them. The sun will eventually swallow the solar system. But that's not to concern us. The range, on the other hand, is greatly affected by A and C. If you can find the maximum and minimum values, that can be very useful, extremely useful for graphing your function. In fact, I recommend when you're graphing your periodic functions to be aware of your maximum and minimum values. Let's take a look at the example we started the class with over here. And we're going to look at f of x is equal to 8 sine 12 x minus 10 plus 4. If we zoom out, we'll see that its period was 30, but its maximum here, what are the maximum values? How did that happen? Oh, there it is there, 12, 12. So the maximum seems to be 12. So I can put that line in, y equals 12. And I like to graph these little lines with dotty lines is nice. Okay, done. And then let's duplicate that. And the other line, the minimums, they happen down here at negative 4. Okay. Now the task for you right now is to tell me, where did these lines come from? 12 and negative 4. How can we find the values 12 and negative 4 inside that function? 8 sine 12, x minus 10 plus 4, blah, blah. Where did those come from? The maximum being 12, the minimum being 4, minus 4. Can I read those anywhere in here reliably? Where did it come from? Yes, you could be the one to figure it out yourself. And if you figure it out yourself, you never need to forget it. Because if you forget it, well, you can just figure it out again. I see this value here, 12 for k, but k influences the period. It's just like an accordion. It doesn't feel like it should be influencing the verticality of like the y values of this function. So where did the number 12 come from? Where did the number negative 4 come from here? Huh? Oh, 12 minus 4 would be 16.
Well, you stretch it so it's like the amplitude is now 8 on the axis, and you add 4, so it has to go up to 12, which makes, is that correct?
So how would you calculate the maximum and the minimum values based on this function?
Add the, like for the maximum, add the A and C, and then put it in the chart.
Kind of, yeah, just about. Lily, you want to say what you're thinking?
The amplitude is 8, double that, that gives you the total range that it has to be. If you know the horizontal axis, it's just for our 8 up from the horizontal axis and 8 down from the horizontal axis.
Yeah. So here, let's take a look at it this way. So here's the horizontal axis 4. Okay, so then the horizontal axis is over here, 4. That's the middle. And we get that from C. So if you know C is the horizontal axis, there you go. And then you go 8 above that. You just add 8, and that will give you your maximum. If you subtract that, because you know sine's minimum is -1, so you'll be -1 times 8. And so you'll be down there, and there it is there. So you go your horizontal axis, your C plus or minus A. C plus or minus A would give you the maximum and the minimum. That's really useful for graphing. You absolutely want to have those points precise. Where does this function reach its maximum? Where does it reach its minimum? And so on. And then that will really, it's something that I will be looking for to see is your graph accurate. You want it in your table of values, and you want to figure out a strategy to get it in your table of values. If you use the table of values for your parent function and transform it point by point, absolutely you want to include sine 90, sine 270 in that table of values. Absolutely you want to include cosine 0, cosine 80, 180 in your table of values. Transforming those points will give you the maximum and the minimum. Carrying on. So they have that here. Minimum is C minus A, the maximum is C plus A. So this is like, if you get that little formula down, that way when you're graphing them, you can put your ... along there. Okay. So this is the function that we're going to work on together, and we're going to create a graph of this function as a class. And then, we're not going to have very much time to practice today, are we? My goodness. All right. It's a good thing we're budgeting 2 days on this topic. Might need a little bit more. Tell me, what's the amplitude of this function? F of x is 2 sine 3 multiplied by x minus 60 minus 2. What is the amplitude? Good. What's the period of this function? 6. Sorry? 120. Why is the period 120, Adriana?
Because it's 360 divided by 3.
Yeah, here's our k value. And to find the period, recall that that's 360 divided by k. So 360 divided by 3 gives you 120. And then visualize that. Imagine your 360-degree circle and your 160-degree angle, your 160-degree angle, your 160-degree angle, and see that it's like a kind of almost like a Mercedes-Benz sign or something. Good. What's the phase shift of this function? What's the phase shift here? Yeah. Shifted by 60 in which direction? Shift 60 to the left or right?
Right.
To the right. And let's also find the y-intercept. Okay? And we'll do it this way. How do I find a y-intercept? If you didn't learn about periodic functions today, but you took this point away and didn't forget it ever again, that would be a class well spent. How would you find a y-intercept of a function? You sub in 0 for x. So let's calculate f at 0. Okay? F at 0 is going to be 2 multiplied by sine, bracket, 3 multiplied by 0 minus 60, end bracket, minus 2. Let's keep going. F at 0 is equal to 2 multiplied by sine of 3 times 0 and 3 times minus 60. 3 times 0 is nothing, so we don't need to worry about that 0. What's 3 times minus 60? Thank you. It's negative 180. Who gave me that answer? Oh, it was me. Why are you all so slow? That's my question. Why? It takes longer when you're like waiting for your classmate to answer. If I'm asking these painfully obvious questions, I appreciate your attention, but it's okay to be a little bit more boisterous. And then I'm going to subtract 2 from the result. So notice what we've done. We first did this. We did 0 minus 60 to get minus 60. Then we've done the multiply by 3. Now we need to calculate sine of negative 180. Sine of negative 180, visualize negative 180 is the same as positive 180. What's the sine of 180? 0. Yes. So we're now doing the sine of negative 180. The sine of 180 is 0. The sine of negative 180 is 0. And your calculator will tell you the same thing. Unless your calculator's in radians. I don't know what that is in radians. Okay, so this is 2 times we have now evaluated the sine. It's 0 minus 2. So what is f at 0? 2 times 0. So now we do this multiplication. That's 0 minus 2, because we have still this minus 2. Notice that minus 2 is the last layer of bedmas, and it was hanging out outside the party until the bouncer finally says, come on in, and turns out the minus 2 is the star of the show. It's actually the answer. Cool. So that is the y-intercept. F at 0 equals minus 2. Circle it. That's your y-intercept. Cool. The vertical shift. What's the equation of the axis? What's the vertical shift? Down 2. And the equation of the axis? Lovely. The domain, x is of the reals. I'll get that one for you. There's no limits on the domain. The range, what are our maximum and minimum values here? Yeah, the maximum is 0. The minimum is negative 2. So if we wanted to write that as a range statement, we could say y is of the reals, and negative 2 is less than or equal to y is less than or equal to 0. And then we finish our squiggly bracket. So this function actually starts at its minimum and is going to go up and then come down. And if we just use this, we can already get a pretty decent graph of it. Let me show you how. Without doing table of values, without doing nothing else, just evaluate all of the different meanings of the A, K, C, and D. Here. So there's our answers. That matches what we had. The range, minus 4. Oh yeah, right. It's not minus 2. It is minus 4. Yes. We have a mistake. So it's good to have these things in there. Our mistake is our minimum is going to be negative 2 minus 2. So we have to subtract a from minus 2, and that will give us negative 4. Yeah. It sounded good, but it wasn't right. So our minimum is actually minus 4. The reason is c minus a gives us the minimum. C is minus 2, and a is 2. So it's minus 2 minus 2. That gives us minus 4. So that's our minimum. So minus 4 is our minimum there. So now let's go ahead and, oh, right, I have that over here. No, I don't. Oh, I need to make another PDF. Pardon me. All right, so let's go ahead and get sketchy. So over here, we're going to, we know that the amplitude, we know all these things. Could have written them down here. 2. The period was 120. The phase shift was right 60. And our y-intercept was 0. So, wait, it was minus 2. Yes. The vertical shift, minus down 2. The equation of the axis is y equals minus 2. And the domain and range we had going from negative 4 was less than or equal to y, was less than or equal to 0. So here's what I suggest you do. On your graphs, you could use, say, a different color for your maximums and minimums. Go ahead and indicate where the maximum is. This is what I would do. This is my favorite strategy, is using the anatomy of what you know rather than working point by point. You could verify point by point, but this is the way I would do it. and boop, 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 boop along there. And then go ahead and even put the axis on there. So that's at -2. There we go. So now we already have 1 point here. The y-intercept is -2, so go ahead and put that on. Okay. We know we're working with x and sine x, so we could actually fill in a table of values for our parent function. We know that when x is 0, sine x is 0. When x is 30, sine x is 1/2. When x is 45, this is 1 over root 2. When x is 60, this is root 3 over 2. When x is 90, then we have 1. And then we also have another point where it's 0 at 180. It hits its minimum at 270 and its maximum at 360. Sorry, it's back to 0 at 360, not its maximum. It's a horizontal axis there. So this point here we can find. This point here we can find. This point here we can find by applying transformations. So apply transformations to a few points, and then maybe take some of your 30 degrees, your 120 degrees, 150 degrees, it's also 1/2. So find a few of these easier ones and transform those. You don't have to transform all of them. You'll be there all day. So let's go ahead and figure out our transformation point. If you recall, we can take points that are like x, y in the parent function and transform them to what I like to call a transformation point that looks like x divided by k plus d and a multiplied by y plus c. So we can do that over here. So I have here my k is 3. So I'm going to take my x values and divide by 3, and then add 90 to those x values, because I want to shift them in the positive x direction by 60. Sorry, add 60 to those x values. So here's what's happening to my x values. I do x divided by 3, and then I add 60. And then I look for my y transformations. They're multiply by 2 and then subtract 2. So I'm going to take my y values and multiply them by 2. So I'm going to have 2y minus 2 there. Okay. Now let's do that to some of these points. 0, 0 is going to go to 60 minus 2. Okay, cool. So I can put that on my graph right away. Here's 50, 60, boop, right there. And then 30, 1/2. Okay, 30 divided by 3 is 10. 10 plus 60 is 70. All right, cool. And then 1/2 there. Okay, 1/2 times 2 is 1. 1 minus 2 is -1. Cool. Okay. And then let's skip these because they've got weird fractions and radicals for now. We can come back to them when we want a little more detail. Oh, we can put this point on as well. 70 minus 1. So we're already at 70 and we're up here at -1 up there. Cool. This is -2. This is -1. Great. This is -3. Okay, I know where my -1 and my -3 are. Great. And then we have 90, and sine x is at its maximum. So if I do x divided by 3, that's 90 divided by 3. That would be 30. 30 plus 60, oh, we're back to 90. All right, now take the y value. 2 times 1 is 2. Minus 2 is 0. Oh, that's where this function is hitting its maximum. Notice, sine was hitting its maximum there. Our transform function is hitting its maximum there. Same. So that's it hits its maximum at 90. It's right there. And then I'm going to do something a little sneaky. I know that these things are symmetrical around their maximums and their minimums. So I can take this point over here. Let me zoom in and show you what I'm thinking about. I know visually that this point is going to be symmetrical around that point. So I just go ahead and put it over here. Wait, over here. And then this point's going to be symmetrical around that as well. So I'm expecting to find those points there and there. All right, let's see if I get that when I transform point by point. Okay, that would be 110 at -1. Let's see if one of these points will do 110 and -1. I'm going to guess it's this one here. Okay, 150. I take 150 and divide by 3. That's 50. 50 plus 60, that's 110. 1/2. 1/2 times 2 is 1. 1 minus 2 is minus 1. Ah, wouldn't you know it? Working visually and working point by point gave me the same point. So I'm very confident that I've got a good graph so far. Now, to be honest, I've got so much of this pattern here. Whoop, and it goes up and it's really close there for a little bit. And then it comes down, boop. That I could just reflect that down here and work visually and go ahead and use what I know about the period here. So I know the period is 120. Here's how I can use the idea of 120 in this case. I know that here I have 60. If I add 120 to this point, I'll get another point that's just the same. So 60 plus 120 would be 180. And so 180 is right there. I know that everything is going to repeat between that and this over here was the point 120. 120 minus 2. Let's see if I find the point 120 minus 2 if I work with 180. Okay. Now I should finish one idea. This is 120 minus 2. So that would be add 120 to that. That's 240. So there's 240 minus 2. So I expect that this is all. And then what about this one? That's 90. Add 120 to 90. That's 210. So that'll be over there, 210. And then, and then let's do this one. That's 70. And then I add 120 to it. That's 190. So that'll be there. And then symmetrical around that. So that'll be there. And then I just go ahead and repeat the little bits. I don't have to work point by point ad nauseum. And then I know, well, in between these two, I'm going to hit a minimum. I expect to find it there at 150 because they're symmetrical. And then if I go over there, that should be on it, and that should be on it. I'm just working purely visual now. I'm not looking at numbers at all. And I've got a good graph. Oh, that wasn't very good. That was a little too pointy. Maybe I could change that by just rounding it out a little bit like that and using my eraser on there. Okay, so that's applying what I know about the period to just extend it and add on. Let's see if those points that I got were correct. So I found this point, I found a minimum at 150 minus 4 working visually. Let's see what happens if I take 270, the minimum of sine, and apply my transformations. So I take 270, I divide it by 3 here in my little formula. 270 divided by 3 happens to be 90. 90 plus 60 is 150. So that's my new x value. And then minus 1 is the y value for that minimum. 2 times minus 1 is minus 2. Minus another 2 is minus 4. Oh, good. That was the same point I got here. 150 minus 4. Just working visually. Just saying I know that's going to be between these 2 points where it crosses the horizontal axis. And I know my minimums because I already calculated them. To me, this is the easiest and most intuitive way to use your knowledge of AKC and D to work a little bit point by point and a lot working with amplitude, horizontal axis, and the idea of maximum and minimum to graph these things. After this, I just say, well, I notice that up here we are at 210, and then we go down to 240. So it takes me 30 degrees to go from the horizontal axis to the minimum. So I just go over another 30 degrees and pop that point down there. And then I go over another 30 degrees and I hit the axis again. And I go over another 30 degrees and I hit the maximum again. And then I just link it with a beautiful curve, as beautiful as I can draw. And then put an arrow to indicate, yeah, that continues doing that thing off to infinity. And hey, it sure would be nice to have this y-intercept on there. And oh, wouldn't you know it? It's going to hit a minimum right there. I could go ahead and calculate it, but I don't even need to because visually I'm so confident that that's correct. There, and that's our graph of this periodic function. And that's how I would do it. That was my method. Now, if you want to work point by point the whole way through, that's going to be okay. You could also feed your function x values. Don't even worry about the parent function, just feed your function x values. However, this is a little bit of a horror story. I have seen some students last year feeding it the x values 0, 1, 2, 3, 4, and 5, and being like, oh, it's just like a line like this. And you never see the periodic behavior because you haven't fed it nice x values. You'll need to look at your function and know I need to at least put that sine value through 360 degrees of worth of x values. So you need to know something about the period of this function, at least x values between 0 and 120. The problem with that method is how do you find the maximums and minimums? I'm still not exactly sure how you guarantee you do that. So that's why I recommend this method as the best way to graph your periodic functions. Oh, we're in here. Yeah. So this is some of the steps. One of the ways is you can graph the parent function, state a table of values for the parent function, and apply transformations to obtain those map points, and then plot the transform points and connect all the points. Okay. Yeah. So that's one way. So now go ahead and try. Let's get another example. Yeah. So here are the textbook problems that you can practice to get some work on this. Thank you for your certainly your uninterrupted attention. Yeah, during this lesson, I do really appreciate it. I know it was a longer lesson than we usually have. I think we kind of needed it with this this topic. Was that okay? I was like kind of like, how am I doing? Feedback. It's like, okay. I didn't like. Anyway, talk too long. And what to say about that? Yeah, tomorrow we'll be looking at the same topic again, but a lot more time for practice and how you work the opposite way. When I show you a graph and say, find me the equation, how do you pull out your A value, your K value, your C value, your D value? Spoiler, the D value is the hardest one to find, but if you're good at finding the y-intercept in one direction, you can use the y-intercept in the opposite direction to find the D value. And that'd be my preferred method algebraically. You can also do it visually. So that's for tomorrow. Try these for now. And any questions, absolutely hit me up by email, Team Learn at Home. And it's been a slice, everyone. Bye.